Good morning, one and all. Today we discuss about 14th chapter, that is nuclei. What is the nuclei? Okay, in the previous chapter we know about the atom. In atom, small space at the center with positive charge is called nuclei or nucleus. Atom having small space with positive charge at center, that is the nucleus. That is atom. In the previous chapter we discussed. Okay, now we discussed about the nucleus. Nucleus is nothing but strongest force in a atom is called nuclei. The strongest force is nothing but the strongest force in the nucleus, in the center of atom is called nucleus. That is why, because nucleons or nuclei having consisting of some neutrons and protons. Nuclei. So this is only this we can choose only. This is the nucleus. This positive charge is neutron. This positive charge is proton. This proton is neutron. Neutral charge is neutron. Okay, it is a attraction force in between them. It is the strongest force. Okay, it is a nucleus. Is a nucleus. This is a atom. Inside the atom, nucleus having small space, that is a positive charge. The nucleus consisting of are made up of neutrons. The neutron, protons. This is proton, neutron, proton. Some of the neutrons or protons inside the nucleus. That is the nucleus having strongest force. Nucleus is nothing but strongest force in the inside the nucleus. That is strongest force in atom. This is the atom. Strongest force in the atom at center is called nucleus or nuclei. It is because strongest force due to neutrons or protons. This is neutron, proton positive charge, neutral. Okay, between them attraction force is attraction force. This attraction force is nothing but in the inside the nucleus. It gives a strongest force inside the nucleus. Okay, in this chapter we can discuss about properties of nuclei or nuclear size or nuclear mass or stability of the nucleus and nuclear phenomena and radioactive properties and nuclear fission and nuclear fission. Okay, now discuss in this chapter. Now nucleus is made up by number of protons or neutrons inside the nucleus is called nucleon or nucleus. Okay, nucleus is representation of the nucleus is like this: X, Z, A. What is the A? What is the Z? It is a representation of the nucleus. Okay, Z is the atomic number. That is the atomic number. A is called atomic mass number. Atomic mass number is the atomic number. A is the atomic mass number. What is the atomic number? What is the atomic mass number? Okay, now we discuss about atomic number. Atomic number is denoted by Z. Okay, atomic number is denoted by Z is nothing but number of protons. Number of protons is nothing but P. Number of protons inside nucleus. Number of protons in the nucleus is called atomic number. It is denoted by Z. Okay, that is Z is equal to P. that is number of atomic number is equal to number of protons. That is the atomic number. Now next, atomic mass number. Atomic mass number, it is denoted by A. What is the atomic mass number? That is total number of nucleons. Total number of nucleons in the nucleus such that protons and neutrons inside the nucleus. Inside nucleus is called atomic mass number. Atomic mass number, that is the A. Atomic mass, that is total number of nucleons, is nothing but A is equal to Z plus pre, that is number of atomic number plus atomic number is equal to atomic number plus number of neutrons or protons, number of protons or number of neutrons is called atomic mass number. Is the relation. A is equal to Z plus N or P plus N. Z plus means number of atomic number plus neutron number. Number of protons or number of neutrons is called atomic mass number. Okay, now we discuss the first topic, that is 14.22 in this chapter, atomic mass and composition of nuclei. Composition of nuclei. Okay. Atomic masses. The mass of the atom is very small. The mass of the atom is very small, and also atom having small space at center, that is a nuclei, and also atom having small mass. Okay, that is atom having small mass, and also nuclei having small mass compared to, that is atom is higher, the inside the nucleus having small mass or small density. Okay, now atomic mass can be measured or in the masses unit, that is can be measured in the case of atomic mass unit, that is AMU. Atomic mass unit, that is the unit of mass for nucleons or nuclei. The mass of the nucleus is measured in the form of atomic mass unit. Okay, one atomic mass unit is equal to mass of one carbon C612 atom by 12 is equal to 1.992647 into 10 to the power of minus 26 kgs by 12. Okay. Now we get one atomic mass unit is equal to 1.660539 into 10 to the power of minus 27 kgs. It is mass. Okay, mass of the nucleus is measured in the form of atomic mass unit. One atomic mass is equal to 1.660539 into 10 to the power of minus 23 kgs. Okay, it is the mass of the nucleons measured in the atomic mass unit. One atomic mass is equal to this much, 1.660 in 539 into 10 to the power of minus 27 kgs. There is a it can be observed by the mass spectroscopy or mass spectrometer or device. Atomic mass of the various elements, some of the elements having different atomic mass unit. Different elements having different atomic mass unit. That means different element having different masses. Different masses is nothing but different atomic mass unit. Okay, that is a integral of multiple integral of the hydrogen atom. Hydrogen atom is nothing but one H1. That is a single. Okay, suppose 1H2 proton. Helium 4 to 2He4. That is a alpha particle. 2He4. That is alpha particle. That is a product of multiple product of hydrogens. We can multiply atomic mass unit. Suppose we can example is chloride or chlorine. Mass of the chlorine. Okay, now mass of the chlorine is for mass spectrometer. We can count the mass of the chlorine, that is 34 point experimental 34.98 unit. That is atomic mass unit. In the textbook U is there. That means atomic mass it is done by U in the textbook. Some textbook is in the atomic mass unit, this symbol, and also in the case of some textbook only AMU, or some textbook is U, that is unit of the masses. 34 in the case of chlorine, the mass of the chlorine is 34.98 atomic mass unit, that is 75.4 percentage. The remaining mass can be converted into, that is remaining mass is 36.98 AMU or U, I don't know, B or U, that is the 24.6 percentage. That is a mass of the chloride. Now we can calculate the mass of the chlorine. Okay, mass of chlorine is equal to, okay, this one, see 34.98 into 75.4 plus 36.98 into 24.6 divided by percentage, 100%, we get 35.47 AMU, atomic mass unit or unit whatever may be. 35.47, this is the mass of the chloride, 35.47. it is equal to the atomic mass number. It is equal to A, that is atomic mass number. Okay, that is chlorine, mass of the chlorine is 35.47 atomic mass unit. It is the average value of mass of the chlorine, average mass of chlorine. This is a calculation of the atomic mass at various elements. Now we discuss isotope. What is the isotope? If the neutron number, every element having same neutron number, if the neutron number is same, n is same, that is n is nothing but neutron number is same in every element. This type of elements is called isotope. Okay, example is nothing but here Neutron number is same, atomic number is same, atomic mass number is different. A is different, Z is different, only same N, that is Neutron number is same, atomic mass number is different. This type of elements is called isotope. Best example is Chlorine Kr 8636 and Rb 8737. Okay, what is the how to calculate the proton N? Okay, according to atomic mass number, A is equal to Z plus N. N is equal to A minus Z. Okay, from this equation we can find the number of neutrons. From this equation, from this one, 86 minus 36 is equal to 50. From this one, 87 minus 37 is equal to 50. Here 50, here 50. That means Neutron number is same. Neutron number is same. Here different atomic number or mass number. Atomic mass number or proton number is different. Only Neutron number is same. Okay, this type of elements is called isotope. Another example is barium 9 4, borate 10 5. Here 9 minus 4 is 5. Here 10 minus 5 is 5. Nothing but number of neutrons is same. Proton number and mass number is different. Only same Neutron number is called, this type of elements is called isotope. Now isobars. When a atomic mass number, when the atomic mass number is divided by A is same, for every element, is identical. Same elements is identical. That means any elements having same Z, same A, Z is different, Neutron number is different, only A is same. Some of the elements having same A, different to Z, different to N. That means atomic number is different, Neutron number is different, only atomic mass number is same. This type of elements is called isobars. Okay, example is lead Pb 21482, bismuth 21483. That is the mass number is, atomic mass number is the same, atomic number is different, that is proton number is different, that means Neutron number is different. And also another example, 1H3 2He3. This is the example of the isobars. Okay, only same atomic mass number, atomic number and Neutron number is different. This type of elements is called isobars. Next, isomers. Elements having same A and Z. Okay, all elements or any elements having same atomic mass number, atomic number is same or similar, this type of metals is called isomers. Okay, isomers means iso means similar. Okay, that means chemical properties are same, but this A is A and Z is same, atomic mass number, atomic number is same, but they have different properties, that is the radioactive properties different. Okay, suppose radioactive properties nothing but alpha, beta, gamma, emission ratio is different. That is best example is bromine 8035. This is the best example. We having same Z but different radioactive properties. Okay, now isotopes. Isotopes. Okay, isotopes means when a given given elements have same Z but different atomic number is same, different atomic mass number. That is A is different, Z is same, N is not same. Okay, only atomic number is same, atomic mass number, Neutron number is different. This type of elements is called isotopes. Best example is 1H1, 1H2, 1H3. These are the example of the isotopes. Okay, now we discuss about second topic is radius of the nucleus or size of the nucleus. Size of nucleus or radius of the nucleus. Radius of nucleus or nuclei is the heading. Size of the nucleus is nothing but radius of the nucleus. Okay, you know relation according to the nucleus. Atom size is 10 to the power of minus 10 meters. The atomic size is 10 to the power of minus 10 meters. Okay, size of the nucleus is 10 to the power of minus 15 meters. That is 1 Fermi. 10 to the power of minus 15 meters is nothing but 1 Fermi. That is the nuclear size. Is the nuclear size or size of the nucleus is 1 Fermi. 1 Fermi is nothing but 10 to the power of minus 15 meters. This is the size of the nucleus. This is a relation discussed in the atoms. Relation between the nucleus and atom. How much size of the nucleus, how much size of the atom. Okay, from the alpha scattering we know the distance approach. This is a small big particle, this is a small nuclei, this big particle, the big nuclei. Okay, we can find the distance closest approach. That is the distance closest approach is nothing but D. Here big nuclei having bending is high at nearest to the center. That is the D is high. Here small particle bending is low nearest to the center. That is center having positive charge, alpha particle having positive charge with kinetic energy 5.5 million electron volts for small nuclei and big nuclei. Kinetic energy is same, but here distance closest approach is different. For small particle D is small, for bigger particle D is high. Is only bending is at a large distance, is bending is small distance from the center. From the center both it is smallest distance depends upon the size of the nucleus. That means here is positive charge, here positive charge, both will be repulsion. The small size particle having small positive charge and the attraction force, repulsion force in between them small here. That's why it comes to center. It is nearest to the nucleus. It is away from the nucleus. That is more big nuclei having big repulsion force. Small nucleus having small attraction force. That is a distance approach in between the small nuclei and big nuclei, like this. Okay. Now size of the we can find the size of the nucleus or radius of the nucleus. Okay, according to relation between the density and the closest approach or distance, this is the density of the nuclei. This is the distance approach or radius of the nuclei. That is the its certain distance is constant, like this. Okay, that means distance is at center. Distance approach is decreases. Distance is increases. That is R is increases, density is decreases. Constant and also decreases. Decreases means here nucleus having protons and neutrons at a certain distance is attraction force. Okay, from this center is attraction force, from this is repulsion force. Here more force is given, force is occur at the center. That is the reason nucleus having protons and neutrons, that is the strongest force in between them. That is a constant. After certain radius increases, it can be decreases from the graph. Okay, now according to the relation, density is equal to mass by volume, that is m by v. Okay, m by v. Mass is nothing but atomic mass, that is A. Volume, that is 4 by 3 pi r cube. Rho is equal to is the mass, atomic mass. Atomic mass is nothing but atomic mass number is equal to 4 by 3 pi r cube. Is now r cube is nothing but A by 4 by 3 pi rho. Okay, this is the constant. You can remove the constant, that is r cube is proportional to A. Okay, that is r, from this r is proportional to the e to the power of 1 by 3rd. We remove the proportional, that is r is nothing but r naught into e to the power of 1 by 3. It is the relation between the radius of the nuclei and atomic mass number. R is equal to r naught into e to the power of 1 by 3rd. This is the relation radius of the nucleus or size of the nucleus. Find the from this equation. Okay, now r naught is the constant value, that is the value is 1.2 into 10 to the power of minus 15 meters or 1.2 Fermi. It is 10 to the power of minus 15 is nothing but 1 Fermi, 1.2 Fermi. It is the radius of the nucleus. It is approximately equal to the radius of the nucleus. Okay, from this graph, the density of the nuclear matter is constant. That is, density is independent of atomic mass number. The density of the nuclei is independent of the atomic mass number for all nucleus or R nuclei. Okay, suppose in the experimental, the density of the matter nuclei is 2.3 into 10 to the power of plus 17 kg per meter cube. It is matter nuclei. It is the density of the matter nuclei. It is very large compared to ordinary matter. Ordinary matter. It is a nuclear matter. It is a very large, 2.3 into 10 to the power of 17 kg per meter cube is very large compared to ordinary matter and water or gases. Okay, that is, it is very large. This atom having large space having large nucleus at the center. That is the biggest nuclei. The radius density is more, the size of the nucleus is more. It is depends of the density. Okay, now we discuss about actually we know about the discovery of neutrons, so it is forgot. Okay, now we discuss about the neutron. In 1932, James Chadwick found or observed the emission of neutral radiation when beryllium is bombarded with alpha particle. That is beryllium Be9 4 plus scattered with alpha particle He2 4. You can remove exhibit the emission the carbon 12 6 plus 1 particle, neutral particle, that is a neutron. It was found that neutral radiation exhibit one special particle, that is a neutron. Okay, neutron, that is neutral radiation is nothing but electromagnetic radiation. It emits the photons. The electromagnetic radiations gives the these electromagnetic radiations are natural radioactive elements, and this emits the one kind of neutral radiation. A new type of neutral particle is called neutron. Okay, the properties of the neutron. The mass of the neutron is equal to mass of the proton. Okay, that is the mass of the proton equal to, there are only small decimals. Suppose 1.67, it is 1.66, like this. Mass of the proton is approximately equal to the mass of the proton. Okay, that is the behavior of the proton. Now mass of the neutron is 1840 times greater than the mass of the electron. Okay, and also neutron decay into a proton. That is neutron 1 0 neutral charge 1 is gives rise to proton 1 H1 plus 1 electron plus 1 anti-particle. There is a neutron gives the 1 proton, 1 electron, 1 anti-particle, or it is a elementary particle, there is a neutrino. There is a property of the neutron. This is the properties of neutron. Now we discuss about mass energy relation. Okay, see here, mass energy relation, that is the next topic. Mass energy relation, the Einstein suggested and improved and gives the some relation about the mass and energy. Mass converted into in the form of energy. energy converted into in the form of energy. That is a mass energy relation from the special theory of relativity by the scientist Albert Einstein suggested some relation between the mass and energy relation, that is mass energy converted into mass converted into energy converted into mass. That is a here total energies conservation law of energy. It is E is equal to here formula E is equal to mc square, that is energy form, and in the case of mass form m is equal to E square by c square, that is equation 1 is equal to equation number 2, that is energies conservation law. That is input is nothing but output. Input is nothing but output. Here initial energy is equal to the final energy, that is mass can be measured in the form of atomic mass unit. Energy is measured in the form of mega electron volts. In the total chapter Nucleus, the units of mass in the kgs for substance of anyone, but here nucleus the mass can be measured in the form of AMU, atomic mass unit. The energy is the mega electron volts. Mega is nothing but 10 to the power 6. Okay, every energy in the form of nucleus, that is absorbed energy and binding energy and emission energy, every energy in the form of mega electron volts. In the form of mass, nuclear mass and reaction mass and particle mass, any mass can be measured in the form of AMU, atomic mass unit. Okay, now we discuss one atomic mass is equal to, according to E is equal to mc square. M is equal to mass of the electron 1.6 into 10 to the power minus 27 kgs. Here c square, c is the light velocity, 3 into 10 to the power of 8 square. We substitute and we solve this one, we get 931.75 mega electron volts. That is one atomic mass unit is equal to 931.75 mega electron volts. This is the energy, this is the mass. Mass can be converted into energy, energy converted into mass. There is the mass energy relation. There is the in special theory of relativity, according to Albert Einstein, mass energy relation. It gives the one atomic mass is equal to 931.75 mega electron volts. This is the relation. Okay, from this understand, from this relation it can be applicable for nuclear reactions and nucleons and electrons and other particles. That is energy is conserved for input is equal to output, that is initial energy is nothing but is equal to the final energy. Is the energy conservation of law of conservation of energy for nuclear masses or interaction nucleus. Okay, now we discuss about nuclear forces. Nuclear forces is according to binding energy are the strongest force. Nuclear forces are the strongest forces. Is nothing but nucleus. Inside the nucleus, proton and neutrons is there. In between them, attraction force is there. In between attraction force, from we get it is a attraction force. That is the nucleus having strongest attractive force. Nuclear forces are strongest attractive force in between neutron and proton inside the nucleus. From this graph we can just explain. This is 0, this plus 100, this minus 100. This is R naught. This is R naught is equal to 1 radius in units is Fermion. Fermi. Okay, units of radius of the nucleus is, it is radius of the nucleus. It is the potential energy. Potential energy versus radius. Nuclear forces much stronger than the Coulomb forces. That is, nuclear forces is stronger than the electromagnetic force. It is stronger than the Coulomb forces. It is stronger than the gravitational force. Okay, nuclear force is the strongest force than electromagnetic force, Coulomb force, and gravitational force. That is, the nuclear forces are the strongest attractive force, because in between the nucleus neutrons and protons is there. In between them, attraction force is more compared to the another one. Okay, and also from this graph, it is short range force. It is only below 8.5. R is equal to 0.85. Then it is a 1. It is a 1. It is, sorry, it is 1. It is 2. Below 1, it is 0.85. It is maximum. It is going to be maximum at negative. That means if from the nucleus force between the two nucleons is 0, that means here small distance is very large. Distance between the two nuclei is R is more, the force is 0, and also small distance, attraction force is more small. That is, force is proportional to the 1 by r to the power of 7. That is, according to Coulomb force is 1 by force to the power of r square. Okay, there is a Coulomb force. There is a nuclear forces. That is a very strongest compared to the Coulomb forces from the graph. Okay, we can draw the plot between the nucleus as a function of distance versus potential energy. Potential energy versus distance from as a function of two nucleons. It is the from two nucleons. The potential energy is minimum at r naught. The potential energy is minimum at r naught. That is, r naught is nothing but 0.8 Fermi. This means that force of attraction larger than the larger distance. That means nuclei having large distance, in between them force is attraction force. So nothing but okay. Now here greater than above 0.5 Fermi or 0.8 Fermi, larger than the 0.5 Fermi distance, r is greater than r is greater than the 0.8 r is greater than the 0.8 Fermi. There is a large distance. That is, here the force is attraction force. The r is less than 0.8 Fermi. There is a small distance separated by, that is a small distance, is a large distance. Okay, that is the repulsion force. Okay, according to diagram from the potential difference, potential energy versus distance, from this relation we get go at large distance, the attraction forces appear at a small distance, and below 8 binding energy, below 0.8 Fermi in the nucleus, the repulsion forces occur. So now the third point is Now see here, the nuclear forces between the neutron and proton and proton or proton is approximately same. In the case of neutron proton, neutron proton, like this. Neutron proton These are chemical reactions, that is force between the neutron proton is same. That is it is due to mass of the proton neutron is approximately same. That is approximately same. But the nucleus does not depends upon the electric charge. The nuclear forces are same in between the neutron proton. Why? Because these are having same masses. Mass of the neutron and mass of the proton is approximately same. That is the reason. Okay, but it do not depends upon the electric charge. This proton having neutral charge, proton having positive charge, neutron having neutral charge. There is no charge. Okay, that is unlike Coulomb's law. Newton's second law, gravitation, there is no simple mathematical formula for nuclear masses and also for neutron proton relation. Okay, here from one according to nuclear, some points. Nuclear forces are the strongest force. Number 2, nuclear forces are the very short range force. Third point is nuclear forces are non-central forces. Fourth point is nuclear forces are exchange forces. Okay, it is due to mesons. It is from elementary particle, that is spin dependent. Okay, thank you. Vanada.